Okay, today we're going to be solving log equations and exponential equations. So, for example, some easy ones. 3 to the 2x minus 5 equals 7. Or, would that be an exponential equation or a log equation? That is definitely an exponential equation. Make sure you look at it before you answer. What type of equation would this be? The log base 2 of 5x plus 6 equals 13. That's a log equation, all right. So we're going to learn a bunch of methods for solving log equations and exponential equations. And so what are the biggest methods that we can use? One method for solving a log equation or exponential equation is using something we call the one-to-one property. We've already kind of talked about this. Let's suppose you have two simple exponential functions. So you have one exponential function, the exponential function base A. And I don't know exactly what I am inputting into these functions. Okay, so here's the function, we'll call it f. Some unknown is going in, we'll call it x. The same function, f, a different unknown going in. But what I can tell you is that their outputs were equal. Okay, so I've got two functions whose outputs are equal. What can you automatically tell me about the inputs? They had to be the same input. Is that true for all functions? No. Okay? If a function is many to one, meaning it fails the horizontal line test, any function that has a failed the horizontal line test can produce equal outputs from different inputs. Okay? It's still a function, but it's not one-to-one. It fails the horizontal line test. But if you have a function which is one-to-one, which exponentials and logarithms are, then you are guaranteed, if the outputs are equal from a function, then it had to have been the same inputs to begin with. So if you can make, if you can make a log equation or exponential, some exponential base A equal to some other exponential base A, you just set the exponents equal to each other and solve. So if we can use our log rules and exponential rules to rewrite the equation to look like this, well, we can just drop the exponentials altogether and probably end up with a much easier linear equation. Same thing with logarithms. If you can rewrite the equation using our log rules, which we learned yesterday, we can rewrite it as a much easier equation. Now, is it going to be possible to rewrite all exponentials so that they are of the same base like that? No. For example, up here, here's an exponential base 3. Can I rewrite the number 7 as a base 3 power? I mean, technically you can, but not easily. So we would not use the one-to-one properties to solve this equation here. So instead, we use a property of logs and exponentials that says, if I compose them together in either order, then they will do what to each other? Cancel, because they are inverse functions. Okay? So one thing I might do to solve a log equation is input each side of the equation. You are literally taking each side of the equation and plugging them into some function that's going to cancel them away. Right? So let me show you an example of that. Let's suppose we have 7 to the x equals 12. Okay? I'm going to take both sides of this equation, 7 to the x, and I'm going to plug that into some function that I know is going to cancel it down to just x. And whatever I do to the left side, I better do the same thing to the right side. So 12 is going to get plugged into that function as well. And then whatever comes out is going to be what x equals. That's the idea. We literally take both sides of the equation, plug them into the same function. Because the function is one-to-one, I'm guaranteed if these inputs were actually equal, then their outputs will also be equal. And now I got x by itself, it's straight. So what is this function that's going to cancel 7 to the x? Log base 7 of x. Get up. Okay, and so that's literally what we do. We plug both sides of the equation into the log base 7 function. What if it was a log equation to begin with? What if we have the log base 3 of x equals, I don't know, what number have you always wanted to know what power of 3 it is? 32? Sounds good. I'm guessing it's 3 point something, right? Bigger than 27, less than 81. I need to create a function such that when log base 3 gets plugged into it, it outputs just x. And then, because I have to plug 32 into that function as well. And then I know the outputs will be equal. What is this function that I can plug log base 3 of x and 32 into that will cancel log base 3 of x? It's the exponential function 3 to the x power. Typically we call this exponentiating both sides of the equation. But what you're literally doing is you're plugging both sides of the equation into an inverse function. Okay?
Wait, how do you know that means x is inverse?
What's the definition of a logarithm? It is the inverse of an exponential. They are inverses of each other by definition. So if you have a log base 3, 3 to the x is its inverse. What is the inverse function for log base 13 of x? 13 to the x.
What if there was like a 2 in front of the log?
If there's a 2 in front of the log, then first thing I do is divide both sides by 2,
Oh, okay.
then figure out the inverse function. So you want to get that log part by itself first. Yeah, good stuff. All right, let's start solving equations. Here we go. Some of these are pretty easy, and you don't have to use inverse functions to solve them. Oh, you're not raising your hand. You're giving the answer. Very nice. Yeah, and a lot of these are common sense, but I still want to, for the purpose of teaching, spend some time talking about it. 2 to the x is actually equal to 2 to the what? 5th. Right? See how I was able to rewrite both sides so that they're both powers b? Both sides is an exponential function base 2. Okay, so I've got some exponential function base 2, where x is its input, and it outputs something. I also know that when 5 is its input, it outputs 32. I know that their outputs are equal, so what has to be true about their inputs? They must be equal. So I take the input of the left side, which is x, and the input of the right side, which is 5, and now I get this equation, which is a solved equation. That's pretty easy. Now, how could I have solved this equation? So, what method did I use here to solve this equation? That's the one-to-one properties. Okay? How could I solve it using inverse functions? What could I do to both sides? Take the log base 2 of both sides. So log base 2 of 2 to the x, and then log base 2 of 32. So this gives me x equals, what's the log base 2 of 32? 5. Here's a major flaw I see with this method. Does your calculator have a log base 2 button? Will your Friday calculator have a log base 2 button? No. So how in the world would you solve an equation where you have to use inverse functions, but you don't actually have a button on your calculator for that inverse function? Well, you could use change of base. You're correct. We could rewrite this as natural log 32 over natural log 2. Absolutely, that's always an option. But do you know what my favorite method is? This might sound crazy. Okay? If I'm presented with an equation like this, I just go ahead and natural log both sides right off the bat. And I know what you're saying. You're saying, Dramble, that is crazy. But, here's my number. No, I can't help it. Every time I say crazy now, it's like channeling Carly Rae Jepsen. Are natural log and 2 to the x inverses? No, they do not cancel each other out. But I do have a log rule that says I can do what with this exponent? I can bring it down. So we end up with x equals natural log, x times natural log 2 equals natural log 32. This is now to get x by itself, I just divide both sides by natural log 2. And voila, we have x equals natural log 32 over natural log 2. So what method is that? That's not using inverse properties. That's not using one-to-one properties. That method is just using log. Take the natural log of both sides and use your log rules to simplify it down. And you end up with the same answer you would have had you done change of base, right? But,
GPDs have a natural log on them, don't they?
GPDs have a natural log and a common log, LOG, LN. Yep. I always like LN. I think it's one less letter to write. Kind of preserves the lifespan of my hand. But I'm always amazed at how many students think it's IN, not LN. I see that on quizzes a lot. And I'm like, natural log. Log. The daughter can tell me what letter that starts with. Okay. What's the answer to B? That was ridiculously easy. Let's look at C. I could take example C, and I could rewrite, what? You end up with natural log x equals natural log 3. So x equals 3. Let's look at C. 1/3 to the x equals 9. Can I rewrite the number 9 so that it is also an output of the exponential function 1/3 to the x? 1/3 to the negative second power. So we have two functions. I know their outputs are equal. So therefore, what must be true about their inputs? They must be equal as well. And hey, there you go. There's your solution. Okay? So that's what solving using the one-to-one properties would look like. Or you could have taken a log base 1/3 of both sides, or taken natural log of both sides. And so you have x equals natural log 9 over natural log 1/3, something like that. Yep. For ones that easy, no. Now, if you really like solving by using those one-to-one properties, could you use them to answer part D? Not really. No, I mean, technically, can I rewrite the number 7 as e raised to some power? Yeah, in fact, it's e raised to whatever the natural log of 7 is. But if you're going to be doing that, you might as well just take the natural log of both sides to begin with, and what do you know, x equals the natural log of 7. So, okay, pretty good about these simple ones? Why not? Just type it in your calculator. I might require you put your answers as decimals just because there's a little bit more skill that goes into being able to do that. 3 numbers after the decimal place, yeah. Don't write 3 decimal places. It makes no sense to me. I've seen students do it before. They're like 2.56.9. I'm like, what is that? That's some version number of software. Wicked. There's probably a setting on there that's rounding to the nearest integer. Usually you want to set it to float. Did you find it? Yeah, we can look at it. Or set it to 3 or 4. That way it's automatically rounding to where I want you to round anyway.
Can you re-explain D?
D? So you've got e to the x equals 7, right?
Yeah.
Take the natural log of both sides. Now, I always use natural log. It just so happens for this particular example, it's even better because what can you tell me about these two functions? They're inverses. When you compose them together, you get x. So you end up with x equals just natural log 7. Cool stuff? All right, let's do some more. Let's look at B. In Kansas, that's actually the halfway point. Oh, that's probably what that thing was.
Time to make let's do that. Fifth period will end at 1:34. Sixth will end at 2:08. It doesn't say what side B will end.
Okay. How do you solve example B here?
First divide by 3.
First, divide by 3. So you get 2 to the x equals, this is 42 divided by 3.
14.
Very nice. Can I rewrite both sides as a power of 2 if I wanted to? No, it's not going to be nice. So one-to-one properties are probably out of the question. I'm just going to do a natural log. So we can take a natural log of both sides. So we end up with x, natural log of 2 equals natural log of 14. Divide, so you get natural log 14 divided by natural log 2. Bam!
Does that simplify?
No.
Yeah. Doesn't, smaller than 4, bigger than 3. So I'm fix it?
Do natural logs work every time?
Yeah.
What was the answer for A?
Natural log of 72. Okay, how about this one? 4 e to the 2x minus 3 equals 2. First we add a 3 to both sides. 4 e to the 2x equals 5. E to the 2x equals 5/4.
Natural log.
So you get 2 to the x, or 2x natural log 5/4. So you get x equals 1/2 natural log 5/4. Then you can stop right there. That's enough right there to be able to plug in your calculator and get an answer. And that's also pretty. I don't see any reason why you would simplify further. That to me is a good final answer. But I could see some people taking that and making it into an exponent. And what does raising something to 1/2 mean? So you could technically call this natural log of radical 5/2 if you wanted. They'd be the same thing.
How did you know that when we divide by 2 is 1/2?
Divided by 2 is the same thing as multiplying by 1/2. Yeah. I don't know why.
You have stupid questions all the time, right? My turn.
Did she tell you that was a stupid question?
Yeah, she did. I know, right?
Can we be honest with her? That was less stupid than asking what the answer to example A was and laughing.
No, it wasn't.
Either the x equals 72? Oh my
Oh
gosh.
my God, she asked, what was your question? Okay, what's 2 plus 1?
You didn't know.
All right. There's no such thing as stupid questions.
Your math teacher, we have to stick together.
Hey.
We're going to make you a math league shirt.
All right. I'll wear
You
it.
can all wear the same name. OMG, we're twinsies.
I had Math Olympics on the back of my Letterman shirt.
See that. We need extra credit for me. Oh my God, yeah.
On Pi Day.
No. And math league?
No. 2 times 3 to the 2t minus 5 minus 4 equals 11. Add a 4 to both sides to get 2 times 3. 2 times 3 to the 2t minus 5 equals 15. Divide by 2. 3 to the 2t minus 5 equals 15 halves. Yeah, we can natural log both sides. Why not? Or you could log base 3 both sides, but then use change of base later. So this becomes 2t minus 5 natural log 3 equals natural log 15 halves. Agreed? You should not agree with me. That's wrong. Nope, that's wrong. Where? Very nice. Right? You must have those parentheses, otherwise the 3 was only being raised to the negative 5th power, not the 2t minus 5. That whole thing was the exponent. Which creates a problem, because now the variable I want to solve for is inside a set of parentheses. Alright, let's divide by natural log 3. And then what? Add 5. So we got natural log 15 halves over natural log 3 plus 5. And then divide by 2. So t equals natural log 15 halves over 2 natural log 3 plus 5 halves. Cool.
Wait, what? Oh.
You just do 1/2 times.
Yeah, the whole thing, like, put the whole thing in.
Yeah, you could put a 1/2 in front of this log, or a 2 in front of this log, or a 1/2 in front of the whole fraction. I mean, it doesn't matter. When you divide a fraction by 2, you're just multiplying its denominator by 2. And if you wanted to, you could bring that 2 up here and call that a 9, right? Let's call that natural log 9. Any questions? How do you do this one? So I think everybody's instinct is to subtract 2. Go and warn you, this is going to be wrong, but I want to keep going because I want to identify and get everybody out of their system. And what do a lot of people want to do next? They want to natural log it, and what they're actually going to do is natural log this and natural log this separately. And the reality is, you're not allowed to do that, right? That would be distributing a natural log over a subtraction. Now, could I natural log both sides right now? Yeah, that's okay. I have not messed up anything. We'll ignore this major problem right here, since you don't see that. Natural log a negative. But let's focus on this. How do you simplify this? It's a subtraction inside of a log, though. It's not a subtraction of 2 logs.
Oh.
That's
So
the key.
Wouldn't be division.
Nope. Our rule tells us if we have a division in the input of a log, I can make it the subtraction of 2 separate logs. This is a subtraction log. We don't have a rule for that. There's nothing we can do here. But what do a lot of students actually do? They go log, 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 boom, 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 and then they keep going and solve, but that's not right. Okay? We actually just did an exponential equation last week in IB. And the equation was like this. You solved it, you get a solution. If you actually went through and went log, 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 you actually still got the same solution. They purposely did that just so that people would feel comfortable doing the method the wrong way, so they could really see who knew their stuff and who didn't. Because a lot of times people will try this and then they'll be like, no, that can't be. That's probably not right. Let me try a different method. Well, they actually found an equation that worked doing it the wrong method and gave the correct answer still. And I think they actually gave the answer that said, show that the solution to this equation is this. So people got that. They're like, oh yeah, I must have done it right. And then they got 0 points. 0 points. Isn't that crazy? I thought that was a little bit cool. But yeah, the method is completely invalid. Unvalid, invalid. Don't ever go through and log individual parts, even if it looks like it's working out. So now we go back to ground 0, or the beginning of the problem. And we look at that and we try to ask ourselves again, how do we solve that? It's quadratic-like. right? This is something squared minus 3 times something plus something. If I were to replace everywhere I see an e to the x with some new variable, pick a variable. I heard t. 4.
No. I didn't even like 5 hours.
So we get t squared minus 3t plus 2, right? That's a quadratic. And so we factor it. What multiplies to positive 2 and adds up to negative 3? Isn't e to the 2x the same thing as e to the x squared?
Yes. Yeah.
Because 2 times x is 2x. So this becomes e to the x minus 1, e to the x minus 2, and then what do we do with each of those factors? Set the first one equal to 0. Also set the second one equal to 0. So you get the equation e to the x equals 1, natural log both sides. X equals natural log 1, which we all know is 0. This one, you get e to the x equals 2, natural log both sides. X equals natural log 2, which we all know is, yeah, just natural log 2. Is the air right around it? Yeah, usually there's some. Oh, well, that'll do it too. There's some setting on there where you hit a button and then like all these like it should say float 0, 1, 2, 3, 4, 5, 6, and you pick which number you want it to round to. Somehow yours must have gotten set to 1. So our basic factoring method is make sure it's equal to 0. So that when you factor, you set each of these factors equal to 0. So you get this simple equation and this one.
Yeah, we don't understand how.
So you add 1, then you natural log both sides, you get x equals 0. Add 2, natural log both sides, you get x equals natural log 2.
How did you get the top thing into the center one? How did you know those were factors? Did you just
How did I go from this to this?
No.
I just drew some parentheses.
No.
From here to here?
Yes.
What it's a quadratic. What multiplies to 2 and adds up to negative 3?
So did you just pretend he was another variable?
Essentially, yeah.
No, let's just focus on ourselves.
Okay, that's all I got, but I want to make a problem up for you. It's a big important homework. Really, we're not moving on to a new section tomorrow, so really important homework. How would you solve that equation? 2 to the 3x minus 5 equals 5 to the x plus 1. Can I rewrite both sides as a power of 2 or power of 5? Or powers of some other number? Yeah. That one-to-one property is not going to work. Can I take the log base 2 of both sides? Yeah, but what's the log base 2 of 5 to the x plus 1? Those don't cancel. So maybe I do the log base 5 of both sides. Then that doesn't help you on the left side. So no matter what, you're going to have to use that logarithm rule that makes you bring exponents down. There is no single function that is an inverse to both of those. So might as well just use a natural log. So this becomes 3x minus 5 in parentheses times the natural log of 2, x plus 1 in parentheses times the natural log of 5. Ew. Before we even think about how we're going to solve that, let's think about this equation. What if I were to give you the equation 3x minus 5 times 2 equals x plus 1 times 5? How would you solve that equation right there? First thing you would do is distribute. This becomes 6x minus 10, and this becomes 5x plus 5. Well, guess what we should do right now to solve this one? We should take those natural logs and distribute them. Didn't I say you're not allowed to distribute natural logs over addition or subtraction? Yeah, that's not what we're doing here. What are we distributing over addition and subtraction? What operation? This is multiplication. Natural log 5 is a number. We are distributing the multiplication of that number over the addition and subtraction. So that's very different than if I took natural log of 6 plus 7 and tried to call that natural log of 6 plus natural log of 7. That you're not allowed to do. Okay, that's not multiplication. That is the actual log function. Okay. So this gives us 3x natural log 2 minus 5 natural log 2 equals x natural log 5 plus 1 natural log 5. Great. Let's go back to the purple equation. What would your next step be? Add a 10 to both sides? Also do what? Also combine like terms. You're going to subtract the 5x from both sides. You're going to add a 10 to both sides. So you're going to get x equals 15. That's great. Well, guess what I should do on this equation? Yeah. How about we add a 5 natural log 2 to both sides? And how about we subtract an x natural log 5 from both sides? Now, the only problem is, in reality, technically, are these like terms that can be combined? No. So I have to write 3x natural log 2 minus x natural log 5. And are these like terms that can be combined? No. So I'm going to have to write natural log 5 plus 5 natural log 2. Okay, great. I really wish these had been like terms so I could just combine them. But technically they're not. But what is combining like terms actually equivalent to? How would you solve this equation right here if I told you you were not allowed to combine like terms? How would you solve, oops, come on now. Erase. How would you solve 2x plus 3x equals 10 if I told you you were not allowed to you weren't allowed to combine like terms? You weren't allowed to just say 2x plus 3x is 5x. But you still got an x on each side of the equation. What if I factor an x out? What's 2 plus 3? Isn't combining like terms actually factoring? It is. You factor out the part that is like about them, and then the parts that weren't like should add together. 2 and 3. They're not like, but they add together because they're just regular numbers. Well, we want to do the same thing here. Factor the x out, and that leaves you with 3 natural log 2 minus natural log 5. And yeah, those aren't like, they can't combine, but haven't I, in a way, combined those two x terms so that I'm now physically writing x only once? Yeah. That's the goal. Now I can just divide all of that junk in the parentheses, and that is our final answer. Oh, I think it's beautiful. I think it's beautiful, but I like lots of ugly things. I mean, I enjoy my 2-year-old.
That's what I thought.
What? Did you just call my wife ugly? Whoa! Matt!
Yeah, but we both came in 8th grade, yeah.
Oh, really? You guys think they're in middle school? Okay, so that's pretty wicked, right?
Yeah.
Pretty crazy. Wicked. Yeah, I'll just go ahead. We'll call it a day.